Let's talk a little bit about the electromagnetic spectrum. And this page should be in your handout as well. So when you look at this, it's sort of cool, but it's a little confusing. So let me say right up front, for my class, you do not need to know any of these numerical values. They're very interesting, but we're not getting into them. All right, what you do need to understand is the relationship between wavelength and energy and frequency. So we'll go over that. And then the other thing that you need to understand is the different types of waves that exist and their relative placement given the other types of waves that exist. So let's back up and say, so what are we talking about when we're talking about the electromagnetic spectrum? We're talking about light here, but we're talking about much more than light. And in essence, we're talking about energy. And this energy is coming in the form of, some people say waves, and some people say particles. There's far more discussion on that than I'm capable of relaying, but just know that they could use either term in discussions, and the way I've been told you can sort of resolve the fact that they're referring to them differently is that these are like particles that are coming on waves the way a grain of sand might come in an ocean wave. So you can think of it sort of as a particle with a wave-like function. Okay? So, but know that these emanate from the sun. They emanate from different sources. Here we can create electromagnetic waves from different types of equipment that we have on Earth. Okay? All right, so let's talk about the different types of waves. There are long, lazy waves. And by the way, this is not showing the progression of one wave. This is just showing the relative frequency and wavelength across the spectrum of waves that are available. All right, so first we've got radio waves. Radio waves are very long and very lazy. They can, if it's a very clear night, travel quite a distance and still be interceptable and discernible by our radio equipment. All right, there are even radio waves coming from various places out in outer space that we have grand telescopes, or rather, what are those called? You know, the great big dishes that are collecting those and trying to decipher them and see what on earth they mean. All right, whether they're just noise, energy noise, or something more meaningful than that. So know that these happen and that they're very long and lazy. Right now in the room you sit, there are all sorts of radio waves going through that room, through its atmosphere. If you had a radio present and you turned it on, you could get all sorts of radio stations. Okay, so that's the first type that we need to know about. The next type are microwaves. Okay, so you can see our wavelength is decreasing, and the way that we measure a wavelength is going from its peak amplitude to another peak amplitude. We would say that's one wavelength there, or we could go from its trough to the next trough. So since it's a perfect sine wave, our amplitude to amplitude values are equal to our trough to trough values. And so we can get a wavelength from that. Okay? Microwaves, when you think of that, we think of all the microwaves that we have in our kitchen, right? And we know that those are useful in heating up food. We know that they would do some level of damage when they are shown on a living organism, right? Right. Okay, next we have infrared rays. Counted in these would be like heat lamps. If you've ever gone out to a restaurant and not all the food for your table is ready at the same time, the cook will take food he's already finished preparing and stick it under an infrared lamp to keep that food heated up until all the food is ready at your table. So again, we're going to a shorter wavelength, aren't we? And as we see the wavelength decrease in size, we notice they're getting more frequent, right? And that's a perfectly proportional relationship between the length of the wave and the frequency at which it meets its amplitude or its trough, right? Okay. Next, after infrared, we have our visible light spectrum. And look at this. You can see infrared is right next to the red portion of our visible light spectrum, right? And then over here, we've got ultraviolet that is right after the violet phase of our visible light spectrum. And we know too that this is sort of the colors in which the rainbow is shown, right? And you may have heard Roy G. Biv as an acronym to describe these colors, right? Red, orange, yellow, green, blue, indigo, violet, right? Okay. Next, we have ultraviolet radiation, UV radiation, most of it that comes from the sun, which is very, very intense UV radiation, is blocked by our upper ozone level. We still have some UV radiation that penetrates the ozone and comes to Earth. It's the least harmful, but we can still get a pretty good sunburn, right? So this is our reason for sunscreen right here. And then our next most, and now we're getting into some really dangerous rays, are X-rays, okay? Again, think about this. My wavelength is getting smaller, right? And my frequency is increasing, right? And then additionally, as our frequency increases, our energy increases as well, okay? And by the time we get to gamma rays, you know, gamma rays can come out of radioactive material, and those can be highly, highly damaging, and indeed they can even be fatal. So here's the electromagnetic spectrum, and again, what I expect you to know is not any of the numbers. I expect you to know what these waves are represented, what a wavelength is, right? The relationship between wavelength, energy, and frequency, all right? And then I expect you to know the names and relative position across these 7 identified areas of the electromagnetic spectrum. All right, so let's work on this real quick. Energy and wavelength have what sort of relationship? And think about this. What I'm looking for in these values is you asking the question, if one goes up and the other goes up, or when one goes down, the other goes down, then that's a direct relationship, and they directly impact each other. However, if when one goes up, the other goes down, the name for this type of relationship, you would think it would be indirect. No, this is evil. It's inverse. So that's an inverse relationship. All right, so given that, we know we've got to plug one of these 2 words in. Let's look at this. Energy and wavelength have what sort of relationship? Well, I see here that as my wavelength decreases, so my wavelength is decreasing, my energy is increasing, right? I've got very little length here, very high energy, and therefore this is an inverse relationship. Boy, that's terrible writing, but you get the idea. All right, now what about wavelength and frequency? So if wavelength goes down, frequency is going up, right? Right, did I write that right? Yes, wavelength and frequency, I'm sorry. So there you have it. So this is also an inverse relationship, right? Now what about energy and frequency? As energy goes up, frequency is going up too, right? Yep. So therefore this is a direct relationship, all right? Okay, all right, very good. That's what I wanted to cover.